Welcome everybody to my talk about scattering compensation deep tissue imaging. I'd like to thank the organizers for giving me the opportunity to speak about our work here and to contribute to the Sculpted Light in the Brain online series. So yeah, my work will be about two-photon fluorescence imaging with scattering compensation. And here in this graph, you see already several methods that are used in the biomedical imaging field to penetrate tissue and to find out details. We see that nonlinear scanning microscopy already fills here a very interesting gap, which is the combination of a large sampling penetration depth and a very good or very high lateral or 3D resolution. This is partly already filled by nonlinear scanning microscopy because it has nonlinear wavelengths, uses that for excitation that scatter very little, and it uses nonlinear signal processing. And this is a very powerful combination for deep tissue imaging. However, that technique can be extended and can be pushed further into even deeper sample regions using adaptive optic techniques or wavefront correction. And the conceptual idea is simply explained here. Imagine we have our excitation wavefront here in the infrared, and it gets scattered. It's infrared, but still at some point it will get scattered by the tissue and the focus gets lost. The idea is now to engineer the wavefront here in order to restore the focus here and to regain our capability to excite fluorophores. Now, the big question, of course, is what can we do to find out as quick or as fast as possible this wavefront shape here, how to engineer this wavefront. Basically, there are in AO techniques, broadly speaking, two different techniques available. Direct wavefront sensing, which use Schack-Hartmann sensors, for instance, to directly measure the wavefront in one single go. They are usually applied to situations where you have some kind of a guide star available, but that's something that we don't have here. So we are using indirect wavefront sensing, and the idea is here to stepwise learn piece by piece from the signal that we accumulate. So we set our spatial lighting related to a particular shape, measure how much fluorescence comes back, and then we change the shape and so on. A very simple approach to this and is shown here below. Imagine we have here a number of pixels on our spatial light modulator, and pixel by pixel we then step the phase of a pixel such that the light that originates from the pixel interferes at the location of the sample point, beat for instance, with the rest of the light and gives rise to a tiny oscillation. Then we have to find out what the optimal phase is and store this phase on a computer to or set this pixel then to this phase. What has been very early noticed in the field, and this is an example here shown already by Velikov in Moscow 2008, is that it's better to directly update each pixel after it has been measured compared to measuring all pixels first and then at the end of one round trip to update them in one go. This is, I think, kind of intuitive. It has been also shown by Sylvain Giguin's group using Hadamard patterns 4 years ago. So here in this sketch, you also see the difference conceptually between immediate updates that bring you much faster out of the noise floor compared to stepwise update, which is here the orange curve. Now, in the past decade, two particular techniques called IMPACT, developed by Amenkui's group, and F-sharp, developed by the group of Benjamin Yudkowitz, have shown particular noticeable results, I would say, in the field of brain imaging. So both have shown that their techniques are able to penetrate through the intact skull or thin skull of the mouse and to image cells underneath. Yeah, IMPACT is shown here on the left. It's actually pretty closely related from a mathematical standpoint to F-sharp, which is here on the right. I'm going to say a little bit about F-sharp now because this is also very related to our technique. Now in F-sharp, we have basically interferometer. You have a static reference beam that bounces off the SLM here, is focused in the sample, and we have another beam that is steered by a galvo. So the galvo scans a fraction of the energy or the light beam across the static reference beam, and we also phase step the light from the galvo such that we can obtain like an interference pattern step by step as we scan, which exists or basically is a kind of an approximation of the field at the focal plane, which we then need to Fourier transform back or propagate numerically back to the plane of the SLM such that we have an idea of our scattering function. Now, the big advantage of F-sharp is that the speed of measuring these modes here, or the scattering function, is decoupled from the speed of the SLM itself. It's actually quite a nice feature. I can use a high pixel count, low speed SLM here because mode shaping and phase stepping is all done by external electronics and mechanics that can be very fast, like galvos, for instance. Now I'd like to present our technique that we have been working on last year, we are still working on, which we have called DASH, which stands for Direct Adaptive Scattering Compensation Holography. And if I were to explain in a single sentence what DASH actually is, I would say it's a common path version of F-sharp with direct updates. And basically, the layout of the setup is here shown on the right is identical to many other AO schemes. We have here our spatial light modulator conjugated to the pupil plane with a couple of 4F relays and galvos in between. And the SLM is then used to create both a scan beam, which is sketched here in blue, and a corrected reference beam with this sketched here in red. So this is what I meant by common path. So we are not using a microscope interferometer and combining two external beams. We are creating in a digital holographic way or synthetic holographic way both beams in a single hologram. Of course, this is not perfect because we have a phase modulator. We have to take the angle of the field that we actually want to shape, but it turns out to be good enough to ensure fast convergence in the end. This mode shape M can be a plane wave, such as used in F-sharp, but we are not restricted to plane waves. In principle, we can choose any basis that we want for M. For instance, Wernicke modes are thinkable, or particular mode bases that are adapted to a particular sample, for instance. And Cn is the corrected beam, and in the very first measurement, of course, we don't know nothing about our turbidity or the scattering function, so we simply set Cn to an array of ones. We display the first plane wave mode, for instance. We phase step it, and this is done all by the SLM itself. So there you see, in contrast to F-sharp, we need here a fast modulator because everything mode changing and phase stepping is done by the SLM. And during the phase stepping or in the phase stepping process, we find out what the best phase of this particular mode is. And this is now another difference to F-sharp, we immediately update our correction pattern C by adding in a complex way the just tested plane wave mode with its optimal phase to the old correction pattern. Therefore, if we then go and measure the next plane wave, we already have a slightly improved pattern C, which already brings us a little bit out of the noise. I'd like to show you some simulations that compare different methods. We have here DASH in blue, also F-sharp and impact, here red and orange, and you see here already that also the performances of these methods is very similar. We also included a genetic algorithm that has been introduced by Raphael Piston's group 9 years ago now. And further methods that have been discussed in this 2008 Valley Copeland Mosk paper, like the partitional algorithm and the continuous sequential algorithm. Now, for high SNR cases, we see that DASH performs best, and high SNR means that we measure in our first measurement 1,000 photons. Also for medium and low SNR cases, where we measure 100 and 25 photons respectively in the very first measurement, we see that DASH still shows best performance, so fastest convergence. And in the low SNR case, it's actually the last method that still gives a significant signal enhancement within the 8,000 measurements that we have performed in this simulation. An interesting question is, how many photons actually required to achieve a certain level of correction. This is interesting because we have a certain photon budget for the fluorescence available. So if we just use a lot of power, fluorophore starts to bleach. We also start to heat our tissue. So it's very good to trade to use very little light simply. And there we see throughout the parameters pixel dwell times the dash, and all the bluish greenish curves here are basically dash versions implemented with different modulators, which doesn't play a role here in this graph, need only half as many photons compared to F#. Another interesting question is how long it actually takes to achieve this 50% correction level that we have set here as our limit. And there we see that, of course, this strongly depends on which SLM is actually used to implement the technique and what's the necessary pixel dwell time to accumulate a sufficient number of photons. Now we see if dash is implemented with a nematic liquid crystal light modulator, which the fastest one switching around 3 milliseconds from one pattern to the next. We see that for short pixel dwell times, we still have a long total measurement time for one round trip. That means testing each one of 256 scattering modes once, around 4 to 5 seconds here, whereas F# is much quicker here. However, I have to say that for F#, we are assuming here a switching time of 0 basically, and it's a very optimistic assumption because even in F#, galvo motion and phase stepping motion and so on will need at least tens of microseconds. But nevertheless, this is what we compare dash to. What we see here, however, is that if we implement dash with a really fast modulator, a MEMS mirror, and those devices are available since several years actually, or decades almost, they switch much faster, on the order of 50 microseconds or so. And here we see that if the pixel dwell time is around 100 microseconds or less, we are already equally fast as F# is, but remember we use a significant lower portion of photons. And if the pixel dwell time needs to be longer, simply because we need to accumulate a sufficient number of photons, then dash wins also in terms of total measurement time. I'd like to show you now some experimental results, and this slide is showing results from correcting turbidity introduced by scattering tape layer above a fluorescent layer, which is just some fluorophores, just a dye text marker on the glass cover slip. And there we see the corresponding enhancement graphs here on the right. We see here what's very notable, that already after the first iteration, dash gives an enhancement of around 10. We also see this in the respective images here, whereas F# shows here an enhancement of around 2. So this is a very significant difference. In the end, both methods converge to around the same level. Further experimental results from mouse hippocampal tissue. These are fixed slices with a thickness of around 550 or so microns. In these slices, microglia cells have been made to express GFP. So those cells are nicely visible here in these images. We see before the correction, we have a very dim image, and already after one correction, one round trip, so the first iteration measuring like 200 something modes one time, we have a significant enhancement in dash. And an even further enhancement than after 5 iterations in total here. We also, by the way, this measurement has been done at the depth of around 300 to 400 micrometer deep in this slice. If you go even further into the slice, so basically to the maximum available depth, that was around 530 micrometer, then F# in this particular experiment was not converging at all, whereas dash was still converging, and we could still obtain a signal improvement of 7 times after only 3 iterations of the algorithm, so after 3,000 something measurements. Yes, so thank you for listening. I hope you liked it. If you have any further questions, please contact me directly under the email address that's shown here. I would also like to announce that we have a PhD position available, which starts from October this year. So if you're interested, or if you happen to know somebody who might be interested to live and research in Innsbruck in our team, please let him know, or if you're interested, please just write us a message. And finally, I'd like to thank the team that is actually working on this project. First of all, Molly May, who is the postdoc here, doing an excellent job, doing basically all the running the entire experiment. Also, Nicolas Barré, he is very helpful with algorithms and graphic cards implementations. Monica, the head of our department, and Kai and Michaela, our collaborators from the physiology department. And last but not least, of course, also the funding agency, the Austrian Science Fund. Thank you very much, and goodbye.